I'm excited to announce our next speaker, Varun Mohan. Varun Mohan is the CEO and co-founder of Exafunction, which builds infrastructure to optimize deep learning workloads. Previously, he was a technical lead and senior manager at Nuro, where he saw the power of deep learning and the large challenges of productionizing it at scale. Before that, he received a BS and a master's in computer science from MIT. Varun, over to you.
Hey guys, I'm Varun from Exafunction. I'm going to do a relatively, hopefully short talk on how to deploy models at scale, why GPUs, what are some of the issues that GPUs sort of introduce, and what you can do to save some money while deploying GPUs for your infrastructure. A little bit about me, currently CEO and co-founder of a company called Exafunction. We optimize deep learning workloads. We're focused on inference, work with some large autonomous vehicle companies that run inference workloads at scale. And we thought it made sense to hopefully generally go over some of the complexities in running inference workloads. So just a super high level agenda here. To start off talking about why folks even use GPUs for ML deployment. It seems like in general, there's a lot of questions around this. Lots of fairly large companies still deploying models on CPUs at scale. There are some clear trade-offs. So where do the actual inefficiencies arise when you're doing this? And how can you actually go about solving these problems in a relatively easy, but some of the approaches are a little involved. So why GPUs? We'll just go over some really quick numbers here. GPUs align, at least on the ML inference side, align really well. It's kind of obvious for a lot of folks why GPUs make sense for training, at least for deep learning training. Workloads are really batched already, and GPUs have a lot of compute. Even on the inference side, though, depending on what kind of operations you're doing, GPUs are extremely parallel arithmetic computation devices. Inference workloads, at least like for vision workloads and NLP workloads, still do a lot of math, right? They do a lot of arithmetic operations. And in those cases, GPUs have a significant advantage over CPUs. So just some ballpark numbers here. These are really general. There's some more details here as well. But if you were to compare a single GPU compared to a single CPU core, you have between 2 and 3 orders of magnitude more compute available. And even if you dollar cost average, CPUs are way cheaper. If you're able to get the most out of a GPU, we're talking about getting, over 10x compute per dollar if you use a GPU versus CPU. There's maybe some, other things to maybe think about, and we'll go over details of why batching is so important. But even though GPUs have 100x compute, the memory bandwidth that a GPU has compared to a CPU is not like 2 orders of magnitude more. It's depending on if you're using an inference or a training chip, it might be an order of magnitude. And because of that, you can actually see a lot of cases where GPUs are not worth it if you're not taking full advantage of the compute. We'll talk about some approaches later on. So what are some of the issues? Why when folks are using GPUs, are they not seeing the kind of performance they think they should really get? That's, I guess, the $1 million question. So one of the sort of big problems that companies sort of face, at least when we work with them, is they have mixed resource workloads. What this means is they have workloads that are running things on the CPU as well. And what ends up happening is, in a lot of the times, you have like very idle GPUs. Maybe like, for some context here, one workload that we're pretty familiar with at Exafunction is autonomous vehicle simulation. You're basically trying to get the code that ran on the vehicle to run in the cloud. Obviously, the code that runs on the vehicle has a lot of compute-bound elements. You're also at the same time reading potentially sensor data from blob storage, so you have network components too. And what ends up happening is, if you were to tie the CPU to the GPU, in other words, every simulation that you run, you basically allocate a fresh GPU. The CPU and network is basically going to block the GPU. We've seen utilization numbers that are as low as like low single-digit % utilization numbers. One very interesting fact, though, is even those CPUs, CPU, you would think that the CPU workload is maybe not as massive as the GPU workload. Obviously, in cases like autonomous vehicles, the CPU workload is massive. One thing that is true is every 2 years, NVIDIA reliably puts out a GPU that's twice as fast. Those kind of wins aren't really seen on the CPU side. So every year, you can imagine there's more the CPU work ends up dominating the GPU time if you were to use the same machine, right? And I guess what this ends up leading to is really poor utilization numbers. And if the code isn't changed, it ends up leading to worse utilization numbers over time. And this is maybe one of those things where, if you're talking about getting single-digit % utilization on the GPU, you're basically throwing away a lot of money. Another maybe problem that a lot of companies, face is kind of spiky workloads. Hey, if you have a very spiky workload, you want to keep sort of P95, P99 latency as low as possible. So you allocate machines based on the P95, P99. And I guess in general, people view GPUs as maybe a little harder to scale compared to CPUs, where people feel like there's way more capacity. What you end up getting is a case where you end up over provisioning the number of GPUs by a good deal. Classic example is, let's say, e-commerce during the holiday season. Maybe another thing to also think about is on-demand compute for GPUs is really expensive. I think at least for A100s, you're talking about a single A100, depending on your cloud provider, costing $20,000 to $30,000 a year. That's usually not how expensive CPUs are, and also at the same time, GPUs are you can't get a 30th of a GPU. There's stuff like MIGs that let you have sort of virtualization of GPUs, but for the most part, it's not very easy. And if you end up using on-demands for the GPUs, whereas you can use Spot for the CPUs, the cost differential could be 2 orders of magnitude compared to the CPU and GPU. And it could actually end up being the case where, you are spending more on GPUs than CPUs, depending on sort of the workload there. Maybe another thing to consider is, hey, you have real-time considerations, and if you do, you can't just batch arbitrarily. Yeah, GPUs are really good at batching computations, but you don't want to just be basically grouping as many requests as possible and throwing away latency. And I think the fact that GPUs have a little bit of a different programming model there makes it harder to use compared to a CPU. If you were to take a model let's say a BERT model that's used for natural language processing, you don't need to think about batching that much because the CPU doesn't get massive advantages from batching similar to the GPU, which means, hey, the way you process it is just get a request, process it immediately. Makes the programming paradigm a lot simpler, basically. Another common, issue that we've seen is, BERT models or natural language processing models are generally, they lend themselves to fine-tuning for different tasks. We've seen enterprises that not only fine-tune for different tasks, but fine-tune BERT models per company that they serve. So you can imagine you get into a state where you have, hundreds, thousands, a number we saw from, some large enterprises was in the hundreds of thousands of these BERT models. And you can imagine, you do this incorrectly, you end up spinning up a GPU for every single one. That results in horrific underutilization, basically. Maybe one other last thing to note there is, the ideal scenario is you want to be able to pack a bunch of these machines, models together. But GPUs also have, relatively low amounts of memory available on them. If you take something like a T4, which is a common GPU used, you basically have somewhere around 16 gigs of memory. Whereas for CPUs, you can get very high amounts of memory. You can get a CPU machine that has potentially a terabyte of memory. So because of that, ideas of packing sort of become a little harder. And this is also why, for workloads that get poor utilization, the solution of why not just replicate your application many times ends up becoming hard to maintain, basically. Finally, depending on the workload, you can actually get, massive network costs, not only from, the bandwidth perspective. You can also get massive costs on the egress side. So maybe one thing to think about is, let's say you have a video processing workload and you want to take these decoded frames and do a lot of processing on them. One common issue you can sort of run into is you decode the frame, but you end up sending it to like a machine in a different zone. And maybe some of the numbers that might make sense is per gigabyte that you send, you basically are you pay like a cent an hour, a cent per gigabyte. And whereas like for a GPU, like let's say it's an on-demand T4, you're paying 35 cents. I guess a T4 in an hour can take well over 35 gigs. So in a lot of cases, we've seen companies that pay more for the network egress than they do for the underlying GPU itself. And this is maybe one of the complexities of decoupling your workload versus like just running the computation right on the same node, right? So some solutions, right, for some of the issues that we had before, like, hey, you have a lot of idle GPUs, figure out ways of basically, the ideal abstraction is somehow like a shared GPU serverless abstraction. We published a post on this a while back, but figure out a way to the ideal solution is figure out a way to basically multiplex many computations across many different applications on a single GPU. The benefit there then is, you're no longer tying a single CPU to a GPU, which has many sort of problems attached to it. Maybe another sort of thing to think about there is, instead of obviously always capacity planning for the peak, intelligent auto scaling is kind of critical here. You want to be able to scale GPUs up based on utilization. One of the tricky parts here, though, is for the autoscaler for GPUs is scaling them, I guess, in a kind of consistent way is a little bit harder than CPUs because the prevalence of GPUs it's a lot more scarce. So sometimes you might need to do more clever autoscaling strategies, but autoscaling is basically a must to basically be able to compete with CPUs, I guess. And then obviously, on the expensive on-demand side, usage of Spot is pretty key, right? Using Spot instances on GPUs basically gives you a 3x win in terms of cost. Obviously, the trade-off is whatever you ran on the GPU needs to be fault tolerant, right? Otherwise, your application is not going to be in a good state. And architecting the system in such a way where you can actually get that fault tolerance is maybe challenging depending on how you implement your solution, right? I think the trade-off here is you get to basically run on Spot, but maybe you need to figure out ways that even if the remote machine dies, you can basically be able to continue operations. Maybe one other thing that's sort of pretty important here is stuff like dynamic batching is pretty critical, right? I think that's maybe the high level takeaway for real time operations. It's as mentioned before, GPUs have greater than 100x the compute as CPUs available. So clearly, you want to be able to batch as much as possible to be able to hit your SLA. We noticed, I guess, some posts maybe a couple years ago from Roblox regarding how they were running workloads, billions of BERT inferences a day on CPU, and some of the common issues that they, I guess, talked about here were basically CPUs being, I guess, easier to manage because hey, you're already running CPUs everywhere. But one of the things that they sort of noticed was they didn't get as much advantages basically running on GPUs. And I think potentially one of the issues is you need to be a bit clever about how you're going to batch some workloads. Like let's say you take a workload like an NLP workload where you're running BERT inferences. One of the problems that ends up happening is each of your inferences might be on a variable length sort of input. And one of the problems there that can arise is if all of your inputs are different length and you want to compute it in a batched way, you might need to pad a lot of your inputs to be the same size. But if you do that on the GPU, you might be throwing away a lot of compute. And you might need to figure out ways of being able to, without padding, be able to run a lot of inferences in a batched way. But one thing is for certain though, because at least for NLP and recommendation style models, because they don't do a lot of compute per I guess inference, to saturate the GPU's compute, you need to do batching. And this goes back to the point I talked about earlier, which is that GPUs have maybe only an order of magnitude more memory bandwidth than a CPU, but they have 2 orders of magnitude more compute. And what this means is for every single weight that you end up reading, you need to be able to do hundreds of computations or tens to hundreds of computations to be able to saturate the hardware. It is cool to basically see companies like Snapchat and Pinterest have started running some of the recommendation and serving systems on GPUs. Some of the very interesting things that they had to do were obviously very smart forms of dynamic batching. This plot over here shows sort of what scaling they were seeing for dynamic batching for Snapchat. And I guess 2 things maybe come to mind here. One thing is batching on CPUs doesn't provide nearly as much of a win, whereas batching on GPUs provides a tremendous win, basically. One interesting takeaway from both of their posts were that they were able to actually reduce latency running on GPUs. And that's once again because GPUs are so good at parallel processing. But part of it is it does complicate the batching logic. One other takeaway from, like, let's say Pinterest was actually that if you run a lot of these models at, you run some of these recommendation models or some of these serving models, the CPU actually ends up becoming a bottleneck to run the models itself. So they needed to employ kind of complicated tricks like using CUDA graphs and stuff to make sure the CPU wasn't a bottleneck. So I guess that's another takeaway, which is that optimizing the actual way that the model runs is actually pretty critical for throughput reasons. And yeah, a completely unoptimized model could actually could make it more efficient to run CPUs. And it seems like looking at some of the results that Roblox had running models on CPUs, that potentially if they had optimized the model, it might have made more sense to run on GPUs. But it does take work and some level of expertise, basically. The other idea finally is to sort of optimize these workloads is in the case where you have many infrequently run models. The ideal scenario is finding ways to basically dynamically place different models on different machines based on usage, right? The dream scenario is a model is getting a lot of usage, scale it to tens, if not hundreds of GPUs. And if a model is not getting much usage, share it with place it on a GPU with many other models, right? And some of the complexities of building a system like that is you also don't want to own the GPU for obvious reasons. Some other interesting facts are, frameworks like TensorFlow and PyTorch, just by the virtue of existing, end up eating a lot of GPU memory. So you need to come up with, I guess, ways of maybe sharing, making sure that the frameworks themselves don't use a lot of memory. And then obviously kind of, I guess, far you can go is you can even place all of the models on CPU memory and swap them in and out of between CPU and GPU memory as necessary. That solution actually ends up working quite efficiently. Like if you think about PCIe bandwidth being greater than 16 gigabytes a second, a BERT model being a couple hundred megabytes, you should be able to swap these models in tens of milliseconds, which is pretty cool actually. But yeah, it does require some amount of engineering effort, basically. Yeah, and then finally, coming back to maybe the network cost side, you want to be able to somehow reduce round trips, right? Egress costs are high, but at the same time, network bandwidth is limited in some cases. And I guess since GPUs are quite expensive, you want to figure out all the ways that you can basically saturate the GPU. And some ideas that we employ at Exafunction are always making sure the scheduling that we do for GPUs are zonally aware of where the clients are. What that allows is you can end up scheduling GPUs in such a way where you pay no egress, right? It does mean you might need to spin up more GPUs than necessary, but if you limit the set of zones where your clients run, that's totally fine. The other sort of ideas we end up having are, ideas like on-the-fly streaming compression, decompression. For some of the autonomous vehicle companies we work with, they send over sensor data. A lot of the time, a lot of the data just, is empty or the same value. And being able to very quickly on the fly in a compressed way, stream data back and forth provides us, over an order of magnitude win in terms of latency and bandwidth, actually. And that's like an interesting trade-off, right? You don't want to end up spending like a lot of time doing the compression on the client side and burn a lot of CPU as well. And then finally, another interesting idea is keep the data on the remote machine for as long as possible if you're running a computation on a GPU. Instead of copying the data back and forth, see if there are ways of like running things, keeping the data on the remote GPU as long as possible. Some of the interesting things we can actually do at Exafunction are we can even offload an entire decoder, run the decoder on a remote machine, decode the frame remotely. So now you're only passing encoded frames over to the remote GPU. Encoded frames are effectively like, they're potentially 100x smaller than decoded frames. So yeah, decoder remotely, and then take the decoder frame, pass it to a detector, and we can do post-processing in such a way where you can have like a stateful pipeline running remotely. And if a machine dies at any point, we can reconstruct the state of whatever's on that GPU and another one, which allows us to also get tremendous advantages from spot instances as well. So basically, to summarize, GPUs do have a lot of complexity attached to them, but if you can actually leverage them properly, there's potentially even higher than an order of magnitude of savings, of cost savings and scale latency savings that you can actually get. Some of the ideas that we talked about here: dynamic multiplexing, intelligent auto scaling, making use of spot whenever possible. Obviously, you can't use spot in all scenarios. There are cases where you do need the availability. So then you need to figure out ways of, having on-demands or reserved instances, and then having some excess capacity of spot instances, dynamic batching, co-locating models as much as possible, and then, figuring out smart network strategies so you don't end up, getting bottlenecked by the network to saturate the GPU as well. So I guess, now a little bit about us. I think, so far we've built sort of services, and our main service is called Exadeploy, which effectively virtualizes GPUs to run computations at scale. We've sort of, ended up working with some of the most sophisticated ML companies to offload their inference workloads. We manage sort of thousands of GPUs, run hundreds of billions of inferences a month at the moment. And what we're actually truly excited about is looking at all the advances in the large language model space, or the foundational model space. And we're going to start, I guess, building infrastructure and potentially even products that revolutionize how people work with these systems. And really excited to share our progress as we move forward. So stay tuned. Thank you for listening. Hope you guys enjoy the rest of TransformX.